Okay, so let's continue with our discussion from last time. We were discussing about audio classification. We have an input which is audio waveform. Let's say it is 10 seconds long and you split it into different windows of shorter lengths. Now, the output is of this sort, whether it is some event is present or not. So this slide helps to understand it a little better. So here you have uh, uh, one problem could be, given this sequence, just tell me whether a given sound, let's say horn, is present or not, right? We call it as binary classification problem. Given this sound, it could be silence mostly, right? Here it is all silence. You don't know it, but I'm just marking it so that here some horn, here it is silence again. And this is the input to my some classifier or detector, and it is just horn equal to true or false. So what is the probability of horn given my input sequence X? This is my input sequence X, right? Which is the waveform. Or you could extract some features like MFCC features, substral features, LFB features. All these features can be extracted and you're feeding it into your, and ultimately you want to estimate whether probability of horn equal to true is large or not. Right? This is called binary classification or detection, binary detection problem. Right? That's what I mentioned here. Probability of horn given X. Now there could be a scenario where in this snippet there could be multiple events possible, multi-class classification. So there could be like the same audio. It can either have a horn or it could have um, um, clapping, or it could have, I have chosen some horn, bell, cuff, clap. These all, any different classes could be present. So you say it has one of these classes. So C could be either a horn or a clap or so on or nothing, right? My input will be either of these four classes or nothing, like or comma, sorry, or nothing. That will be a multi-class classification problem. So you want to estimate probability of C given X. X is your input sequence. Probability of C given X, where C is one of these categories. It's called categorical distribution, or so probability of C given X, where C can take 5 values. It's like it's a PMF. It's also called categorical distribution. Okay, a quick question. How many unknown parameters are there in this distribution, P of C given X? How many parameters are there? You remember, like if you define a distribution, the distribution has some unknown parameters, right? So for example, a Gaussian, one-dimensional Gaussian will have how many parameters? You have all studied Gaussian, right? One-dimensional Gaussian, normal of X given. How many unknown parameters are there?
Two.
Two parameters are there. This one and this one, right? And similarly for this, how many unknown parameters will be there? Yes. Somebody?
Only X.
X is given. X is the sequence, input sequence, the waveform. So your probability of C given X is basically it will have C can take 5 values, right? It will be equal to some A1 for C equal to horn, some A2 for C equal to clap, some A3 for C equal to some other class, A4, C equal to some other class, and A5 for C equal to none. This is the PMF, right? So how many unknown parameters are there? How many unknown parameters are there?
5.
5. But there is a constraint as well, right? What is that constraint?
A1 plus A2 plus A3 A4 5 sum में जो होगा
Summation equals to 1.
1.
Right? And of course, all AI is greater than or equal to 0, and okay, less than equal to 1 anyways is there. So for all I, right? These two constraints are there. So how many unknown parameters are there now? How many?
5
Unknown, pardon?
5 unknown.
See, there are 5 unknown parameters, but then there is one equation which tells you something about those parameters. So total, how many unknown will be remaining?
4. 4.
4, yes. Because you can estimate the fifth one using the value of these 4. If I know A1, A2, A3, A4, I can estimate A5, right? Just 1 minus A1 plus A2 plus A3 plus A4, right? So 4 unknown parameters are there. Okay, just it was a small exercise. Okay, now let's come to next kind of problem where you know the X and it can contain multiple classes, right? It can have clapping. So this, let's say this is clapping. This is cuffing, somebody's cuffing. This is silence. Means actually silence need not be annotated. So now what I want to estimate is what is the probability of clap, comma, cuff, comma, horn, comma, so on. This joint distribution. Probability of horn, comma, bell, comma, clap, comma, cuff. Because in the same audio, we can have these multiple classes present, right? This is called multi-label classification. This is called multi-label classification. Okay, any questions? Okay, let's move on. So now you have this joint distribution, but if you assume that these events are independent. Okay, let me ask one question. Should I ask that question? Okay. If I have 4 classes here, because sorry, cuff, clap, horn, bell, then this distribution will have how many unknown parameters? How many unknown values will be there in this distribution? This is a discrete distribution, right? Each one can take values true and false, true or false, true or false, right? So how many possibilities? Probability of clap equal to true, or basically I will just write in order so that I have to write less. Clap is true, cuff is true, horn is true, bell is true. Probability of clap is true, cuff is true, horn is true, bell is false. Right? You can, like that, you can keep writing. How many cases will be there?
10,
16.
Pardon?
16.
Huh? 16, yes. 2 to the power 4 equal to 16 cases. So we have 16 parameters. So is it true that we have 16 parameters?
No, 4.
Any other answer? Is it true we have 16 parameters here? There is a constraint. What is that constraint? Let us say I call this as P1, this as P2. Then summation over all Pi will the sum will be equal to
1.
1, and given and Pi is greater than equal to 0 for all I. Yeah. So this is the constraint which reduces one parameter. So total number of parameters is
15.
15. Very good. Okay, but still this is a large number. Can we reduce it? If we assume independence, so with independence assumption, with independence assumption, what do you get? You get probability of clap, comma, cuff, comma, everything given x. Oh, there was a given x here. This can be written as,
Product.
yes, product of clap given x, horn given, cuff given x, horn given x, and bell given x. So how many parameters are there now? To define this distribution? To define this distribution, how many parameters are required? Okay, I think in the first problem,
4.
this binary detection problem, how many parameters were required? How many parameters were required here?
4, 3.
In the first problem, which is binary detection or binary classification problem.
1.
1.
One only, yes. Because probability of horn equal to true is some P1, probability of horn equal to false is some P2, but sum of P1 plus P2 is 1. So we get only one parameter. So now come back to this one. Number of parameters here is? This will have one parameter. This will have
3.
one parameter. This will have one. This will have one. 4. Right?
1.
All right.
Yes, sir.
Okay. So let's move on. So now to estimate these parameters for the probability distribution, to specify my distribution, I need to estimate these many parameters, or these many values I have to estimate. To estimate them from x, to estimate probability of clapping given x.
Sir.
Pardon?
Hello.
Yeah.
Shouldn't it be 3? Because again, the constraint, the summation should be 1.
What is the constraint? Summation over?
Probability for a given x, it should be either clap, cuff, horn, or bell, and all summation should be unity.
Okay. Like this.
Yes, sir.
Is this condition true?
So shouldn't we take into account that none of these events happen?
That will be already covered, no? If clap is false, cuff is false, horn is false, bell is false, then that condition is covered. Right? That case is already covered.
Yes.
Okay, now my question is this true? Is this equation true? Does that hold for independent events?
No, sir.
No. Yes, it will not hold. This is not correct. Because cuff and clap are independent, you cannot say their probability will sum to 1, right? If they are independent, right?
Okay. Okay, got it.
Yeah, these are independent distributions, but you can say probability of clap equal to true given x plus probability of clap equal to false given x.
That should be.
This condition holds. That is why instead of 2 parameters, we have 1 parameter here. Right? Okay. This holds, but this does not hold. Okay. So to estimate the parameters of my distribution, I use a model. It could be any model. It could be a Gaussian mixture model, deep neural network, anything. Like there are so many kind of classifiers which are available, decision tree, etc., which I can use. So ultimately, I want to estimate these quantities, probability of either depending on what problem is at hand, whether it is this problem or this problem or this problem. I just need to estimate these parameters of the distribution. So I can use a deep neural network or whatever, right? Gaussian mixture model, etc. I will skip this part because these are required to understand deep neural network. I will skip this part. Now coming to evaluation. How do you evaluate your model? To evaluate my model, I will first train the model. Like if it is Gaussian, you all have studied Gaussian mixture model, right? You all have studied Gaussian mixture model. Is that correct?
Yes, sir.
Okay. So you train your Gaussian mixture model on one part of the data and test it on some other disjoint part of the data. For example, I trained my model on um, uh, let's say in the class there are 30 students. I trained my model on 10 students speech. 10 students speak and I use their data to train my model. I will use 10 different speakers to test my model so that I can assure that my model is able to generalize well, right? Because if I train on, let's say, Giant's voice and I test on Giant's voice, then I'm not sure whether my model will work for Avadhesh or not, right? If my model is uh, performing very well on Giant's data while testing, then I can say, okay, my model is working very well on Giant's data because I trained it on Giant's data, but it may not work very well on Avadhesh's data, Avadhesh's voice. So to assure that my model works not only on Giant's voice but also on Avadhesh's voice, or on any other new speaker's voice as well. So I have to design my training and test data such that training data has got different speakers, test data has got different speakers. Okay. Now, let us say I want I want my model to work only for Giant. I'm not worried about others because others are not going to use my model. I'm preparing a model only for Giant. Then what will I do? I will train on. I will let's say I have 100 recordings of Giant. I will split those recordings. Let's say 80 recordings for training and 80 different recordings for testing, because I do not want to test on the same data on which I have trained, right? Otherwise, even if my model gives a good result, I cannot be assured that it will work on new utterances by Jayant, right? So therefore, this split is very important to design if you want to work it on multiple speakers. Now, let us say you have trained it on all the speakers in IIT Kanpur, right? Who are speaking, let's say, English language. And but now I cannot assure that this model will also work on students from some other country, let's say, which have very different accent when they speak. Let's say American students, they also speak English, but my model will not work very well on them, or I'm not sure if it works very well on them because I have not tested it on that kind of data. Right? So that is what I'm saying, that when we design our training and test data, we have to take care of how we split the data, or how do we design this test and train part, so that we are assured of whatever level of generalization we need from the model, right? Um, and how does it translate to the practical utility? For example, if I train my speech recognition system, let's say Alexa, I train it in India, test it only in India because I have to use it only for Indian users, then no problem. But then it will not work very well for American users or German users who also may be speaking English. Okay, so this is clear now that I split my data. Now, how do I evaluate my model? That what is the quantity which I measure to say that this model is this much good or that much good? Like, how do I compare models? For example, Jayant gives me one ASR system, and he asks me, okay, uh, I will sell it for, let's say, 1,000 rupees, and then another student, Avadhesh, comes, and Avadhesh says, "Oh, I will sell it. I will sell my model for 1,500 rupees." So, which model is better? Which one should I take? Uh, so I have to know. I will ask Jayant, okay, what is your accuracy? Jayant will say, my accuracy is this much. Let's say my accuracy is 99%, and Avdesh will say my accuracy is 98%. Then which one is better, right? So given they are testing on the same data. Now, accuracy, how do you define accuracy for this kind of a problem? And or if not accuracy, then what other measure can be used? So what measure we use, that is called metric. So the metric that is used for this problem is false acceptance rate and miss rate. What is false acceptance? So for example, let us come to this let's say binary classification, simplest case, binary classification problem. So you are in, this is again the evaluation matrix. So for binary classification, right, probability of Horn given X, right? So false acceptance means, I didn't, there was no horn, but it still said horn. Probability of my Y hat says that horn was there, while actually my ground truth, let me call it as YD, or just target T, okay, YD. When YD was false. This is called false accept, right? When my, actually there was no horn, but my system said, oh, there is a horn there, right? It falsely accepted the horn, but there was no horn there. That is a mistake. And similarly, I could have miss rate. Miss rate is that my model said there is no horn. Sorry. My model said there is no horn, while actually there was a horn there. Right? This is called a miss rate. False accept is, so the actually the event was there in the real sound, but my model missed it. My model could not detect it, right? Whereas in this problem, event was not there. My model falsely accepted it, falsely detected it, right? These are two measures which can very effectively capture how much mistakes your model is doing. So you can say FA plus MR is my metric. Like you can define it like that, or you can separately report, okay, my model has a false accept rate of this much and miss rate of this much. Okay. Now let's come to our problem at hand, speech recognition. So speech recognition is the input is you are speaking normally, you are speaking sentences after sentences, and the output is what sentence, what are the different words in it, right? Or what are different phonemes being spoken. So let's first define our problem. So we have to estimate probability of word given X, right? Now the same problem which we did for uh, event detection, automatic speech recognition. Now what will be my problem? Probability of word given X. So what kind of distribution will you define now? What kind of distribution will you define? A very simple problem could be just a word detection problem, single word detection, or single word detection or classification. Let's say first single word detection. I will say a word yes. So you just have to tell yes is true or false. Right? Simply a binary detection problem, single word detection problem. So my input is just some audio sequence, and you are saying whether it is present or not. Right? This could be speech recognition, right? This problem is very much similar to the event detection problem which we have seen. But another problem could be multi-class classification, in which now you can have yes, no, or nothing. Right? Your word could be, your class could be yes, no, or none. Right? So you have some speech and you have to just tell what did the person say, whether he said yes or no or none. This is also very simple. It's very similar to multi-class classification problem. But now there could be a problem which is full-fledged sentence recognition. You have to tell the whole sentence. Tell the sentence. For example, I said, yes, yes, no, 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 yes, yes, oh, no, 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 yes. And you tell each and every thing. I said something, long speech, and you have to tell me, I said, yes, yes, no, 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 yes. Something like this, right? How will you solve this problem? If there are multiple words as in a sentence, what do you do then? Any idea? If there are multiple words in a sentence, how do you do? So an intelligent person will say, okay, let us split the whole audio into small, small audios, and we just detect whether yes is present there or not, no is present there or not. Yes, right? If you divide it into small, small, let's say if you know there are 5 words and you know their boundaries, then you can say, okay, let us split and then feed it into similar kind of problem, multi-class classification problem, right? So one idea could be solution 1 could be split into words, split the audio into words. And use multi-class classification, right? This is solution 1. Use this to multi-class classification. Okay, this could be one solution, but where are the boundaries? Nobody is going to tell you where are the boundaries, right? So that makes the problem difficult. So it is called a sequence to sequence transformation. You don't know the boundaries. You just have to transcribe this whole audio into this sequence. So this is a sequence, right? The waveform is a sequence of samples coming in through your microphone, and the output is a sequence of words which are going out. Okay, so that was the problem, sequence to sequence transformation. And that is why sequence to sequence. Okay, that is why we use hidden Markov models. Hidden Markov models are useful for sequence to sequence transformation. Anybody has any questions here at this moment? Okay, so solution number 2. I don't need to write it. Sequence to sequence. So therefore you use. So basically, what is the philosophy? The philosophy is like this. So number 1, you split into windows, split audio into windows, right? You get small windows. Right? Now, what you do, this is step 1. Then what you do, you use this thing, multi-class classification. Use multi-class classification for each window, right? And then what you get is a sequence of, let us say, to classify phonemes. In the last class, we discussed what are phonemes, right? We saw what are phonemes. Like Hari has ha, ra, e, 4 phonemes. Kamal has ka, ma, la, 5 phonemes, right? So these are phonemes. So we can classify each small window into phonemes. So what we get here is, let's say, oh, no, I don't think we saw this example. So what are phonemes? Let me spend some time to explain what are phonemes. Let us say you have Hari, the word is Hari. It is made up of 4 phonemes. If I use Hindi to write, ha, ra, he, Hari. If I write in IPA, it will be ha, he. And when I have Kamal, it will be ka, ma, la. And in IPA, it will be Kamal. If I have a word called Jack, then it will be ja. Actually, Hindi does not have a sound, so I, Jaik. Jack. And in IPA, it will be, this is a symbol for J sound, and this is a symbol for A sound. This is a symbol for K sound, Jack. So these are IPA phonemes. Okay, so now I'm transcribing it into, like, let's say silence, silence, her, then okay, let's say then silence, 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 maybe some silence, then r, e, e, something like this. That's what you get when you have. Actually, this will be also probabilities. Probability of her will be largest. Probability of C equal to her given the window. This is the largest. Something like that. Ultimately, you want to maximize the probability of the whole sequence, right? That is done using hidden Markov models. We will discuss this later. So basically, your DNN or GMM will just give you these probabilities, right? These are the multi-class classification probabilities. And now you have to stitch them to form words or sentences, etc. That is done by HMM. So HMMs will do the stitching part. So this stitching of these you can say categorical probabilities, because this is categorical distribution. Is done by hidden Markov models. And then you have to do furthermore stitching. So actually you can say hidden Markov models plus finite state transducers. Hidden Markov models and finite state transducers. These are hidden Markov models plus finite state transducers. Okay, let us see this step a little more closely. So okay, as we saw, this whole structure is useful for um, speech to text conversion, or in general any sequence to sequence transformation. So this is the typical ASR system, which is conventionally used in all popular ASR systems like Alexa or Google Home. This has been there for many years. This HMMs and FSDs, this combination has been used for many decades now, and it is quite successful. Earlier, people used Gaussian mixture models here, but now they are using DNNs because they are more powerful, simply for that reason. And now the next phase of research is going on, how to replace this HMMs with, again, DNNs. So that is, we'll discuss towards the end of this course. Okay, these are some references which discuss these typical statistical ASR systems. Now, okay, let's focus on this stitching part a bit. So, okay, let us do this stitching part. Let us start afresh. I will give this title of building blocks. The title is building blocks. Okay. Now imagine you have to design an ASR system, let's say Alexa. How many sentences are possible? Let's say in English language. Question for all of you. How many sentences are possible in English language? How many sentences are possible? If I want to make an Alexa or Siri system, it should be able to transcribe the input speech into sentence. So how many different kinds of sentences are possible? Anybody? How many sentences are possible in a language?
Infinite.
Yeah, possibly tending to infinity. Means there is no limit. You can use what is the property called compositionality to create more and more sentences, right? um, so it is a very useless thing to use MCC, multi-class classification over sentences, like probability of a sentence given the sequence X. I mean, this is not possible. It is not possible to model this, right? So we don't use it. Now, let us break it down into words. Sentences are made up of, or sentences can be broken down into words. How many words are possible in English language or any language? How many words are possible in a language?
Millions.
Yeah, millions. It could also be infinite, but nobody uses infinite words, right? Our dictionary is finite. So of course you can create new words as people keep creating new words, but the really popular ones which Alexa will face are typically of the order of millions, right? Now if I have to define probability of word given X, how many parameters will be there for this MCC distribution? Categorical distribution. How many parameters will be there? How many parameters will be there?
10.
Of the order of 10 to the power 6, right? Right? Total number of words minus 1. Right? Just MCC, just remember multi-class classification, which we discussed here. Multi-class classification, or we discussed here. Multi-class classification. How many words are possible? Your number of parameters is total number of words minus 1. Total number of classes minus 1. So this is of the order of 10 to the power 6. Now, this is also a very large number, very large number. Can we reduce it further? Can we break down words into something else? What can we break down it into? We can break it down into syllables. Now, what is a syllable? Syllable means, okay, different topic here. What are syllables? Syllables are the smallest spoken units. Like ka, ka, ki, ku, ku. These are the smallest spoken units, right? These are the syllables. When I say Kamala, okay, people generally say Kamal. In Hindi, nobody say Kamala, they say Kamal. How many syllables are there? Okay, let me take a simpler example first. Let's take Hari. Hari is simpler. In Hari, how many syllables are there? How many syllables are there?
2.
Only 2 syllables are there, right? Only 2 syllables. Let's take another word. Something like prem. How many syllables are there?
2.
Yeah. So this is basically pa plus ra plus a plus ma plus prem. Let's make it prema because in Hindi nobody says prema plus a. Prema. There are 2 syllables. So whenever there is a half, it is also absorbed within that. So this whole thing becomes 1 syllable. This is 1 syllable. There are 2 syllables here. Again, 2 syllables. I just refrain from prem because people generally say this like this, prem. So it is 1 syllable only. Because this last ma it also gets absorbed in this cluster, prem. Because it's ma halant, not complete ma. It's not pura ma nahi, adha ma hai. Okay, similarly now kamal, same thing happens in kamal. Ka mal, ka mal, 2 syllables. But if you say kamala, kamala, this is ka ma la, 3 syllables. So it's very easy to see. In English, it is very difficult. Like if I say Kamal, how many syllables are there? It's difficult to tell. Then Kamala, different number of syllables. In Hindi, it's very easy to see. It's syllable wise written. So okay, so I can break it down into syllables. Now tell me how many syllables are there?
Sir, I have a doubt.
Yes.
Could you explain the relation between syllables and phonemes?
Yes, very good. Good question. So a phoneme cannot be spoken. It may not be speakable, or you may not be able to utter it. It may not be utterable. A phoneme may not be utterable. Can you say Perhalant? Okay, I cannot say. How will I say? I need with this consonant. I need a vowel to be able to pronounce it. But I can say pay. If I say P plus A, pay, like Google Pay or something, pay phone, what is it? Pay, phone pay, something. So they pay. Pay is there. This I can speak, but single per I cannot speak. That is why in the alphabets also we say ka, kha, ga, gha. So everything is ka plus a equal to ka. This is what you can speak. This is a syllable. You can speak it, but you cannot speak an individual phoneme necessarily. For example, you can speak this phoneme a. Like a is a phoneme, but it is also a complete syllable. You can speak it. In general, not every phoneme is utterable. So you need a vowel to combine with it so that it is utterable. Okay. So this is the thing. And then okay. Okay, so I think this part is clear. What are syllables? This part is clear. So tell me now how many syllables are possible. Let us say there are anybody knows how many alphabets are there in Hindi? Exact number, 42 or something? Anybody knows? Can somebody do a quick Google search and tell me how many alphabets are there in Hindi? Something around 42 or something. I don't remember. If there are, let us say, 42 alphabets, then how many syllables are possible? How many syllables are possible? Okay. Until somebody looks into it, I will give another example. Speech. How many syllables are there? Speak. How many syllables are there? Forty-five alphabets. Thank you. So there are 45 alphabets in Hindi. Okay. For speech, how many syllables are there? In English, it is difficult to tell, so I write in Hindi. So there's only 1 syllable. Speech, speak, only 1 syllable, because this is half, it gets clustered into this part. This is the full thing. So it is only one syllable in both. Okay, so I was just giving an example that you can have so many half letters which can also combine with that complete cluster, complete syllable. P is a syllable, but half sa on one side, half cha on the other side, they also get clustered into it, and you get a single syllable only, one cluster. Okay, so how many syllables are possible if there are 45 alphabets in Hindi? Potentially, I think it will be of the order of 45 square or 45 cube, right? Of the order of maybe 45 to the power 3 or 4, right? So it's still a large number. Number of syllables which are possible in a language is still a very large number. Like still it's a large number, still large. Now we further break it down into phonemes. How many phonemes are there in Hindi? Somebody? Somebody can tell? How many phonemes are there in Hindi?
38.
Okay, 38. I don't know. It will not be 45 exactly because there are words like ksha. Ksha is a combination of like this ksha. This is basically half ka plus ksha plus a. Ksha is a combination of ksha. So I don't know how many phonemes. Yeah, something of the order of 45. So maybe 38. I don't know. Okay, so 38 phonemes are there. Similarly, this another alphabet called Jna for Gyan, like you can say. This is also made up of this is the cha cha ja jha no cha cha ja cha nya. This one. So this is also not a phoneme. It's a cluster of different phonemes. Okay, so and also there similarly there is there like so many are there. We can see them later. So number of phonemes is let's say 38. This looks like a manageable figure, right? If I want to say p of phoneme given x, this is of the order of 38, or let's say you have silence also 39, right? So this is a manageable number. So that's what people generally deal with. People generally say, okay, let us take phonemes. So I think with that, we can end today's class. So in the next session, we'll be discussing more on speech and starting with the hidden Markov models. Okay, thank you very much.
Thank you, sir.
Anybody has any questions, then you can ask in the next class because it's already over time.